All right, got the chat window open just in case. Hello, everybody. The reason that I was on a real beach this time last year is because today is my birthday. So you all get to celebrate with me. This is my birthday present, is it? I get to talk about t-tests and z's and null hypothesis significance testing with you guys. That's a birthday present. Yes. But last year we had some frequent flyer miles that were accumulating and some companion passes that were going to expire. And so we did like this last minute trip to Hilton Head Island for my birthday over the weekend and took my parents so that we'd have a babysitter for my son. And that was fun. And I'm really glad we did it because spontaneous trips are a thing of the past now. So I'm happy to be here. Oh, yes, statistics is the greatest gift of all. I totally believe that. So, welcome back, everybody. Let's see, what do we have to do today? First off, a couple announcements. Let me get my screen shared. All right, let me get the, okay, syllabus. First off, I juggled the due dates for homework 1 and homework 2 because we missed the class due to the power outage. I want to make sure that I give you guys a full week after we finish a topic before you have to turn in the homework for it. So we haven't gotten all the way through homework 1 yet. I'm hopeful to do it by the end of today, but just in case we run over into Thursday, I went ahead and pushed back homework 1 to be due the Thursday of next week rather than Monday. So 3 days. That way you'll have a little bit more cushion. And because I had done that, I'm pushing back homework 2 to the Thursday of that week. So that way we're hopefully catching back on schedule. Homework 2 is available. So you can start that as soon as you'd like. It's up, as is your second formative assessment that is also available. None of that we've talked about yet. So if you feel like just putting that off for a little while, that is totally fine with me. But just in case you're itching for something else to do, I wanted to make those things available. We do have, let's see, a quiz to go over today. And by quiz, I mean formative assessment where you get 2 points for writing anything. So I read through the answers just a little bit ago, and it looks like everybody did really well. So no major problems, but just for the sake of completeness, I did want to go over it. So I have this set up so that you can enter multiple entries if you want to. So if you want to go back in and add another, just to write down whatever we talk about for your own benefit, that's fine. You certainly don't have to, but just that's an option for you. So looking at the formative assessment here, number 1, the difference between categorical and quantitative variables. What did you guys have to say about that? So you can talk to me, you can make gestures, or you can do the chat window, your choice. What did you write down?
So for categorical, numbers are labels, and for quantitative, numbers are actually numbers.
Exactly, that's the biggest distinction. Quantitative variables are numbers that act like numbers. Distances between them mean something. They can have special forms, so they may or may not have one or more natural boundaries. So for instance, a binomial variable would be something like a rate or a proportion, where the lowest you can have is 0 and the highest you can have is 1. But in between then, a change from 1% to 2% to 3% means something. You can also have quantitative variables that are truly continuous, so they don't have natural boundaries. Those are rare in the social sciences, but the big difference is that numbers versus not numbers. So categorical is not numbers. We may use numbers to enter the information to make it easier to avoid data entry errors, but they're not really numbers. And special cases of those, we have binary, so when you only have 2 choices. If you only have 2 choices, it doesn't really matter if those choices are perceived as ordered or not because there's only one difference between them. So once you know what proportion of people answered one of the choices, you automatically know what proportion answered the other. Ordinal is still technically categorical, but then there's order to them. So Likert scales, and by the way, that's how you say it, Likert. It's not Likert. It's a guy's name that was named after this. But that's like the strongly agree, agree, neutral, disagree, that kind of thing. Those categories are ordered, but you could debate the relative distances between them. If you have a race who came in first place, second place, third place, you don't know the distance that separated those places. It could be a split second or it could be 10 minutes. The order is all that's maintained. And then nominal is a type of variable where there's no ordering whatsoever. All of the categories are just separate things. And the big difference in that, okay, notes to folks over here. The big difference is that it's okay to think that binary variables are quantitative in the sense that there's only one difference between the two. You don't have to worry about equal distances as you move up the values. And ordinal variables are often treated as if they're quantitative, even though they're kind of not. But the one thing you don't want to do is treat a nominal variable as if it's quantitative. So if I have 1 means married, 2 means single, 3 means divorced, those aren't numbers. There's no more than or less than that applies. So that's the big one that you don't, the big mistake that you don't want to make. Okay. Questions or comments on any of that? Okay, cool. Moving on. Uh, Trying to describe a quantitative variable, 3 features. Everybody had this. So central tendency, mean, median, mode, the same things they were in grade school. Dispersion, so this is the uh, the hand signals that go with it. See, this is why you guys pay the big bucks for tuition, because the people who are just watching my YouTube channel, they don't get the hand signals with the broadcast, right? This is the extra content that your tuition dollars are paying for. They also probably think that I'm totally bombing every time I tell a joke because they can't see your laughter. So I'm only privy to that additional layer of communication. But yes, this idea of dispersion, so how spread out the scores are. And then skewness is the third thing. That's not something that is typically represented in a model. So the second half of the course is getting into models where we predict one variable from another. Skewness is more something to consider in thinking about how you would treat that variable. So if you have a variable that's really skewed, for instance, a count variable where the lowest score is 0 and the count can go on, forever in theory into positive number land, that would be positively skewed or negatively skewed. Yeah, positively skewed in that one. It's which way the tail goes. That's something that you would want to take into account in trying to describe the variable. So when you have a variable that's skewed, the mean, the median, and the mode are not going to lock onto the same place. And so thinking about those as different representations of central tendency can be useful. Likewise, if you have extreme cases sort of out in the tail, those can pull the standard deviation in a way that may not be as representative of the data as if you had a symmetric distribution. And so then an interquartile range is something that you might report in addition to standard deviation. That's the difference between the 25th and the 75th percentile of the data. So those are so-called robust statistics, the median and the percentiles that are they are designed to minimize the impact of extreme values in quantitative variables, I would say. Okay, and we'll talk about standard deviation and standard error in the next question. Thoughts on question 2 with me? All right. Standard deviation and standard error. You guys nailed this. I was so proud. These are very hard concepts, I think, because you're dealing with abstraction and you're dealing with words that sound like they're the same thing, right? If you're deviant, that sort of sounds like erroneous, but they're not the same thing. They're different layers of representation. So we have the sample. So we can talk about a variable having a distribution in a sample, meaning how are the scores basically what are how do the scores appear? Let's say it that way. And you can talk about any one person from that one sample, how far off from the mean they are is the standard deviation. It's abbreviated SD, homework question, when you write papers using APA style, and that's an abbreviation that's just accepted. You don't have to define it. It's S in a sample and sigma in a population. And if you want to then think about that one sample as being one data point amongst a whole bunch of possible samples. So one of you wrote this down in your answer. I really like that. Each sample being its own data point, and each sample has a mean to contribute. The idea that each sample is going to have a slightly different mean, but they should sort of bounce around the population mean if the samples are representative of that same population, that's a sampling distribution. So sample distribution is the people. Sampling distribution is the set of samples that you would have. And that's more of a theoretical concept than a real one because we only collect one sample most of the time. I have fake data, so I can show you things to illustrate it, but in reality, we tend not to have more than one sample. If you are in a situation in which you do have more than one sample, you may be able to do an analysis that's known as meta-analysis. That's a class, couple classes down the road to put a pin in, and that's the idea of being able to aggregate evidence from similar studies. And so meta-analyses try to do essentially a literature review in a quantitative fashion. So we have all these same studies focusing on the same phenomena. To what extent do they converge onto an answer about the phenomenon? So that's meta-analysis, by the way. But that's one of the few instances in which you have access to more than one sample. So samples relative to each other, then, they're going to bounce around the population mean. The standard error of the statistic that we're talking about, so in this case, the mean is all we've got so far. Standard error of the mean is how far off each sample's mean is from the population mean. And it's related to a standard deviation in a given sample because the tighter the people are around the mean in one sample, the smaller the standard error. So the less standard deviation, the smaller the standard error. And the more people there are in the sample, the tighter it is. So more people, less spread out, creates a smaller standard error, less inconsistency of one sample to another. Okay, so standard error is the magic thing that allows us to start talking about what would happen across samples even though we only have one. It's the magic bullet. And the last question, I am looking forward to trying all of your theme songs. So thank you for participating and sending the YouTube links. I only recognized a couple, believe it or not. So don't stop me now. Whose was that? Okay, that's an excellent, yeah, good choice. Tub thumping. Whose was that? Okay, excellent. I liked that one too. So I'm looking forward to getting to know these. I thought I would play along with you as well. So in honor of our pandemic, I'm going to send you mine here and put it in the chat window. That way you can refer to it later on. I found out the hard way that I'm not allowed to play YouTube videos inside my YouTube video. They strike it down for copyright infringement. So I can't play this for you, but I wanted to give it to you. This year's theme song is I'm Still Standing by Elton John, I have decided. So that's what I feel like. Every day that we get through without like anything catastrophic happening is a win. So I'm happy today because we have power. There's no hurricanes in Iowa, although there's hurricanes approaching everywhere else. Um, that's all we got. I'm still standing. So thank you for playing along. I'm happy to be able to check those out later on today. All right. So any questions, comments before we change gears? No, we're good? Okay. Then let me go back to lecture one, do some selective review, and then add to it. So we are talking about the idea of just introducing the process of making decisions involving the sample statistics that you either calculate or estimate. So in the context of, say, a sample mean, we know how to calculate that, right? There's a ready formula that works. In statistics, that phrase is known as closed form, meaning it's just something that you put in the required components to the formula and it spits it out. In more advanced classes, some statistics are not able to be calculated by a closed form formula, and instead they have to be estimated. And that's an iterative algorithm that goes through fairly complex processes involving probability distribution functions to find the combination that make your data the highest or the most likely. So I'm going to try to not switch between those terms, but just know that if I say like a sample estimate, like that's the value that you have. You can either calculate it or estimate it, but if I have a sample mean, that's my estimate. And so we're talking about how to use that information to make decisions. In the context of univariate analysis, so one variable at a time, as a way of introducing this more general decision-making rule set, we're talking about how do you know if a population mean is too far away from, excuse me, how do you know if a sample mean is too far away from a population mean for that to be believable? Basically, we have some idea of what to expect, and where is what we have relative to that expectation. That's what we've been talking about. So two things that we've talked about so far that use the standard error is a confidence interval and a one sample Z test. And I say Z because we're going to introduce a new letter today, our new friend T. So in order to be able to do this, we have to make some decisions a priori. We have to decide what type of sampling distribution characterizes the different values of the sample statistic across samples. And we've got normal so far, but we're going to have another one later today. How wrong we're willing to be. So where's the cutoff for what is unexpected? What is too different to be likely to have come from our expected distribution? And our traditional cutoffs for that, 95%. So 95% of the time would be where what we have for our one sample is within some sort of expected fluctuation or expected based on the standard error. And 5% of the time would be declared unexpected. And then the third decision is whether or not we want to allocate unexpected to both sides or just to one side. So that refers to one-tailed versus two-tailed tests. Do you remember what I said about one-tailed tests last time? Here's another review. No? One-tailed tests? Yes. Voodoo bullshit. That is correct. Yes. Because all of this is supposed to be setting up a decision-making criteria that's ahead of time, right? You have to decide ahead of time where there is a possibility that what you actually got could either be too high or too low relative to some benchmark. And if that is the case, then you need two tails. You need to allocate your 5% unexpected to both sides. One-tailed is when you stack the deck in favor of one side versus the other, and it's rarely, I would say, appropriate. So we looked at computing confidence intervals using the normal distribution, which defines the area. So this is slide 41 here. So if I have one sample and it came from a population with a mean of 10 and a standard deviation of 5. So I made the data up. I know this. So I pull one sample of 50 people. My one sample has a mean of 10.98. It has a standard deviation of 4.6. So my one sample doesn't hit the nail on the head. It's not exactly the right population mean or standard deviation. And we wouldn't expect it to be exactly right. We expect it to be close. So if I want to know if this sample is close enough, I can compute two different things to tell me that it's basically the same answer viewed from two different perspectives. One is a confidence interval and one is a one sample test. Confidence interval is putting a range of uncertainty around a sample statistic. So the middle of these intervals is always going to be what you got for your sample. So right now we're talking about means. So the middle of these intervals on slide 41 is 10.98, my sample mean estimate. The boundaries, the around part, come from standard errors and how many standard errors does it take to get to the percentage that you've decided on. So if I'm using the normal distribution and I want 95% of the time to be the expected territory, then that's where the 1.96 comes from on slide 41. That corresponds to where does unexpected start? It's about 2 standard errors out. And so this interval that results if I were to grab samples from my population over and over and over again, 95% of my samples are supposed to hold the population mean. Only 5% of them would miss it. And in this case, this is telling me that the population mean is inside my interval. So, in other words, my sample is not all that unexpected. If the population mean were not inside my interval, that's unexpected. And so it could be just because it's 5% fluke, or it could be because my sample actually comes from a different population. There's really no way to say which it is with one sample. So the other thing that we can do, which is telling you the same thing from an opposite perspective, is just calculate what is the probability of observing what we got if the null hypothesis is true. So in this case, null hypothesis is what we expect the population mean to be, which is 10. Our new friend Z here, so this is your first example on slide 42 of a test statistic. I'm going to say that properly. Test statistic. What it's telling you is how many standard errors off your sample mean is from the population mean. And so roughly speaking, if you want 95% of the time to be where expected is, it's 2 standard errors. So a Z that is greater than +2 or smaller than -2. So an absolute value. Basically, 2 is roughly the cutoff to where 95% of the time happens. It's 1.96 specifically. But you can get used to eyeballing these things and say, okay, a Z of anything less than 2 is probably going to be within expected territory. So 2 standard errors is what 95% relates to. So in this result, I have a Z of 1.5, which means my sample mean is only 1.5 standard errors away from the population mean. So it's not unexpected given the standard error. All right, get to this picture right here, slide 47. So putting all of that together ahead of time, we carve up the standardized sampling distribution. So that's what Z is doing, is it's taking whatever we happen to find given the exact numbers that we have. So in this case, a population mean of 10 and a sample mean of 10.98, and it's placing those values onto a standardized distribution where we know what values correspond to what area. So the blue here denotes what is expected. A priori, we say, okay, I think that my sample means are going to follow this normal distribution after I standardize to make it so that the 0 point on there is my expected population mean, and 1 standard deviation of the standardized distribution is my sample standard error. Then I compare what I actually got to these boundaries and figure out if I'm inside or outside. If I'm inside, which is the case right here, because I have a Z of 1.5, then I would say that the result is only 1.5 standard errors outside. It's not unexpected. It's expected given natural sampling fluctuation. That's what it would mean. If I were out past a Z of 1.96 positive, so if I had a mean that was too high, or if I had a mean that was too low, out past a negative 1.96, then I would say that my mean is unexpectedly different. And that's where we get into the words significant or not, and reject and do not reject, and all that fun stuff. Okay. Everyone's like sitting back in the chair now. Can I tell you a story? Can I break character and tell you a quick story? Okay, why not? It's actually related, I promise. So I listened to a podcast put together by a couple of people in my field. It's called Quantitude. So you can ask the Google about this quantitude, so quantitative attitude, so to speak. And the people that do it are Patrick Curran and Greg Hancock. They are both full professors in quantitative methods. They are, as Patrick would say, titans in their field. So they're like big deals, right? And they get together every week and they talk about quantitative things and they argue with each other or make fun of each other and all of this. And so last week's episode, they did a pop quiz where they pitched questions to each other and they had to answer off the top of their heads and then they mocked each other's answers, right? And so the idea is that if you have cred as a quantitative person, like you should know the stuff off the top of your head, right? This is like street cred for us nerds. That's how we're measuring this here. And they had each taken a turn answering a question, defining terms that you probably wouldn't come across for another one or two classes from here, right? And they did just fine on those. And then Patrick threw Greg a question that was null hypothesis testing, and he had 90 seconds to answer it. And his response was, and I quote exactly, "Oh, sweet Jesus." So, someone who's been doing this for a good 25 years, right, got to this content on this slide and went, "Oh, God, I don't think I can say this on command without screwing it up." Now, he got it, of course, but just that reaction, like, ugh. Know that you are not alone if you have that reaction to this, and it will stay with you because this is convoluted. It's a system of logic that has some non intuitive parts to it for sure. And the fact that we have this god awful do not reject language that goes with it makes it even worse. So if you're feeling like this is like what, you're not alone. Just know that you're not alone. So the logic here, we don't know what truth is. All we know is what we believe. And we have one sample to get at truth. So we put a stake in the ground and we say, okay, my null hypothesis is this. And my alternative hypothesis is that it's not this, right? It's something else. So I'm saying different than rather than greater than or less than because we're in two-tailed hypothesis land. So you have, for instance, a population mean of 10 as your expectation. Now, where does your one sample fall relative to that? If you calculate your z-test statistic, which is how many standard errors off your sample mean is from what it's supposed to be, the stake in the ground as your benchmark, and it's more than, say, 2 standard errors roughly, then it's unlikely that it came from that distribution. A score that extreme, a sample mean that extreme, that's more than 2 standard errors away from where it's supposed to be, is unlikely to have happened. So we declare it different. So if a result is more than, say, 2 standard errors from where it's supposed to be, that is a reject the null hypothesis. It's too far away from the stake in the ground to be expected. We would say the result is significant. And in practice, all you're going to get on your output is your test statistic and the p-value that goes with it. That's what you're going to get. So this test statistic is saying that my sample mean of 1.5 is 1.5 standard errors away from with the stake in the ground, the 10 that it's supposed to be. And that's not unexpected. That's within the 2 standard error window that I've created with my decision logic. The p-value means that if the null hypothesis were true, so relative to the stake in the ground, I would see a sample mean that different about 13% of the time. It would be further away from the stake in one direction 6.7% of the time, and further away in the other direction 6.7% of the time. Now, we don't know what to do then. If it were actually far away, we don't know what the right answer is. All we know is what we have relative to the stake in the ground, the null hypothesis. We have the luxury of knowing what the right answer is if you have simulated data, but in practice you never know. So it's always these probabilistic statements. If the stake in the ground were the truth, where are we relative to that? And if we're too far away, where too far is roughly 2 standard errors on either side, it's significantly different. It is unlikely that we would get a result that extreme by chance relative to my stake in the ground, which is my null hypothesis. Okay, how are we doing? Hanging in there? Okay, so if all of this works, I should be able to go back to my simulated data and show you how this works across all of the samples, right? Because I made these data and fake people behave really well. So let's see. I'm picking up on slide 50. Okay, so two inferential uses of the standard error, where inferential means that we're trying to go from one sample to what we would expect across multiple samples from a population. We can compute a confidence interval around our result that describes its wiggliness, so to speak, and we can compute a test statistic that says how many standard errors away from where we're supposed to be did we find where we are. And the three choices that we made in advance, where is unexpected start? So 95% of expected, 5% unexpected in both sides. And so far, we've been using the normal distribution as a way of standardizing the behavior of our sample mean across repeated samples. So the normal distribution to characterize the sampling distribution of the mean. So if this all works like it's supposed to, then I should be able to, okay. No, okay, sorry, I got some Zoom doorbells distracting me for a second. If this works like we're supposed to, then what I should find is that if I do this repeated sampling process, then 95% of the samples should have my population mean of 10, and only 5% of the time I should come to a conclusion of reject the null hypothesis, it's too different, if this works. So, did it work? Not quite. What you're looking at is 1,000 samples drawn from my 100,000 fake person data set, my variable, of different sample sizes. And within each of those samples, I measured whether or not the confidence interval around that sample mean contained the population mean. And if I did, it's a 1, and if not, it's a 0. And here's what happens. If I only have 5 people in a sample, only 88% of the samples had the mean in it, the population mean. And it gets closer to 95% as you get up to 50, but it's not quite. So this wasn't supposed to happen. It's supposed to be 95%, and I made up the data, so what's going on? Well, same issue if I look at it from the perspective of making a black and white decision as to whether or not our sample mean is too different from the stake in the ground null hypothesis population mean. So third decision, how confident is one or two tailed test is 2, and then which probability distribution are we using to characterize the sampling distribution? And normal is the only one we've seen so far in this context, so that's what we're using. So same thing, if I calculate a sample mean within each of these samples and I do a z-test statistic using the normal distribution with my two-tailed test, I should only reject the null hypothesis 5% of the time. Only 5% of the time should I decide that this sample mean is too different because they all came from the population. I know what the right answer is. And yet, the rate is much higher. So 11.7% of the time when I only had 5 people, I rejected the null hypothesis. That's supposed to be 5, meaning way more frequently than I thought I should be, I'm declaring something to be unexpected. And that 11.7 is exactly the opposite of the 88.3. That's not a coincidence because confidence intervals and test statistics are telling you the same thing. So if your sample mean, you have your confidence interval that you compute about 2 standard errors around the mean. If your population mean is in there, then your result is not unexpected. It's expected. It's not significant. If your population mean is not in there, then your result is unexpected, is significant, would happen with less than 5% of the time. So this is not what should have happened. These should all be about 5%. So why did it work this way? Well, if we look at these sampling distributions, the blue lines over the top of them are referring to an expected normal distribution. Now that looks like close, right? Like the blue lines trace reasonably well, but they're not close enough as it turns out. So this is the distribution of the z-test statistic. So if I took each of my samples, computed the sample mean, computed a z-test statistic that tells me how many standard errors away from the population mean my sample mean is, and I do that for 1,000 times, these are supposed to have normal distributions with a standard deviation of 1. But they actually don't. For the smaller samples, their standard deviations are higher than 1, meaning that they are flatter. There's more area out on the outside, meaning more times you'd say unexpected than what you would think. So part of the reason for this is because what we're saying the standard error is has error to it. We are already using the sample version of the standard deviation in the calculation instead of the population version. So some of the problem is because of the differences between these last two columns. What you would have when you use the sample version is a standard error that tends to be underestimated, especially in small samples. So the standard error tends to be underestimated, which means that you are too far, you're not out far enough, basically, in terms of maintaining that same area. But that's only part of it. So an easy fix, if I were just a statistics person, would say, well, to solve this problem, to make sure that it stays at 5% reject rate, you just need to make sure that you always use the population standard deviation. Done. Any problem with that? Don't have it. Yeah. I got the one sample. I don't have population anything, right? And arguably my sample's not great, but it's the thing I have, right? It's the thing I could afford because real people are hard to get data from. So yeah, that can't be a problem. That can't be a way to solve this problem. What can be a way to solve this problem though is beer. And I'm actually not kidding. I would say wine instead personally, but the story goes with beer. So if you don't have the population standard deviation to fix this, so it works just like it's supposed to, what do you do instead? Well, this is another instance in which somebody way smarter than me figured this out a long time ago. So what you are seeing is that when you use the sample standard deviation, you tend to have standard errors that are too small, and you tend to have a decision to say this is unexpected too often. So you're too lenient, basically, in small samples. And if you can't use the population standard deviation instead, what you can do is change your sampling distribution. So I say beer to the rescue because this is a true story. A scientist named William Gossett worked at the Guinness Brewery, and he was in charge of quality control. And it takes a long time to grow hops, and so he was in charge of making sure that each batch of hops met some sort of standard. So the testing could take a whole day because, by the way, this is in the 1800s. This is happening, right? So there's no computers and no fancy stuff. So he's doing everything by hand. And each of his batches of hops took a long time to develop, and so he didn't have very many at a time. So he'd have samples of like 3 or 4 collections, so to speak. Those were his people. And so he did this process of trying to make sure that for any one batch, that the hoppiness or whatever the hell measure they have of beer quality, I'm not a beer person, so you'll have to help me on this. The hoppiness was at the level it's supposed to be. And so if any batch came back too different, relative to the stick in the ground null hypothesis it was supposed to be, it got flagged for further testing. And the further testing was longer and more intensive. Well, it turns out that he found out that he had a really high false positive rate, that 3 times more than expected, the samples that he flagged as aberrant, as unexpectedly different than the population mean stick in the ground, that they were actually okay. So he's all like, what the hell? This test isn't working. And so rather than just, maybe having a pint or two and trying to forget about it, he went a different route. And he went and got a graduate degree in statistics that Guinness paid for so that he could derive a brand new distribution that better describes the sampling distribution of the mean in smaller samples. And when he went to publish his results, Guinness had a policy that employees could not publish because they wanted to protect all of their trade secrets. So he had a pseudonym of student, and he called it student's T distribution, because even if you have a pseudonym, you have to name shit after yourself. This is a rule, apparently, back in the day. You'll get to know lots of famous people who name things after themselves in this class. So we'll have Pearson and Spearman and student T distribution. So he derived this analytically, and I think through like brute force simulation before we had computers to do this. And what he found is that relative to the normal, so this is standard normal, a way of standardizing what you got relative to what you expected. Students T takes into account the sample size. And it turns out that the fewer people you have in a sample, the flatter your sampling distribution is. And we saw this several slides ago where we had the samples of 5 look like a relatively flat mound and they started to sort of move to the middle. Even after you standardize, that phenomenon still happens. So rather than using standard normal to describe how many standard errors out we are, we're going to use T instead in honor of Gossett and his beer. The reason that we will always use T is that if you get enough people, T turns into Z, and it's the same damn thing. So it makes a difference if you have smaller samples. It makes less of a difference the larger your sample. And the smaller, I wanted to operationalize for you. Here's a graphic that I made that's showing you what the critical values would be for a T distribution at different levels of confidence relative to Z. So if you look at the dotted lines on slide 58 here, that's Z. So if you want to have a really strict definition of where unexpected is, you don't want to accidentally declare something unexpected. You might want, say, a 99% expected versus unexpected cutoff, where confidence is 99% and alpha, unexpected, aberrant, is 1%. That's the purple line here. The blue line is if you want to have 95% confidence, 5% unexpected, and the green line is 90% and 10%. And so the fact that these dotted lines are completely horizontal means normal don't care how many people there are. It's the same standard for where unexpected begins, regardless of how many people you have in your sample, regardless of how good of an estimate your standard deviation is from that sample that leads to your standard error. The slanty lines here show you what the cutoff is for where unexpected starts as a function of sample size. In this case, it's called degrees of freedom, which is going to be sample size minus 1 in this instance because we had to compute one mean in order to be able to do this. But like if you look here where, say, for 10 people, you need to have a test statistic that is greater than about 2.2, not 1.96, but 2.2 to get to where the 5% of the area actually starts. And this was another table that back in the olden days, you had this in the back of your statistics textbook and you had to look this shit up. Do anyone have to do this, right? Yeah. No. The software understands that you need to use T It figures out what the appropriate cut point would be, and it gives you the exact probability of observing what you found relative to the null hypothesis HO stick in the mud. So if we take our same sample and we substitute in t instead of z, so that means rather than 1.96 is the cutoff, it's 2.01, and it's relative to the t distribution that's flatter because we only have 50 people. Our new probability is 0.1396. So it's very close to what we had before, but not exact. And if we use t instead to compute our confidence intervals across repeated samples from this population, it works. So that is to say, if you have started your homework yet, and there's questions that say, what is the test statistic comparing your sample mean to the population mean? Your results are phrased in terms of t's, not z's. And this is why. If you get enough people, t becomes z. If you don't have enough people, t takes into account that the standardized sampling distribution has more area in the tails and that you need to have a stricter cutoff for where significant unexpected begins. So in this class, you're going to see t for like everything. T is going to show up everywhere. T is a way of taking whatever you got and putting it into a standardized space where no matter what you're doing, you can say if it's past this point on T, it's significant, where this point depends on how many people you have, as well as how confident you want to be. So it works. All right. How are we doing? Been talking for a long time. I got to reload. Questions, comments? All right, so this idea of paying attention to the number of people that you have. This more generally will be known as denominator degrees of freedom. Right now it's just n minus 1. But more generally, degrees of freedom is the idea that to summarize a variable, you can calculate as many independent pieces of information as you have people. So like if I wanted to describe a variable that is, each of us has one value. I could compute the Lisa statistic and I'd say, this statistic differentiates me from everyone else. And then I could compute the Nikki statistic and the Pam statistic, and I'd go on and go on and go on, and we'd each have one. And that would perfectly describe the data. Or I could start with a mean to say, well, this is my best guess for anybody. And then I could refine it from there, saying, well, this is my best guess for people with this characteristic, but I need a different best guess for people with a different characteristic. And then I need to factor into account these other variables, and that's going to further refine what I expect each person's value to be. So degrees of freedom is the idea that you're limited by the number of people you have, the number of statistics that you can use. We start with degrees of freedom is n, the number of people that you have. You compute a mean, that's n minus 1. You compute something else, n minus 2. Compute something else, n minus 3. So another analogy for this, I'm dating myself here, Weight Watchers has this idea of points, like for food, where you have so many points that you can spend in a given day. And when you eat your way through the points, you're done. I grew up in the 1980s where Richard Simmons called this deal a meal. Any other 80s babies in here, remember? Okay, a couple of you. I have the link for those of you who need to educate yourself on 1980s culture. But he had a wallet and it had like cards in it for different food types. And if you ate something that corresponded to that card, you moved it to the other column. And when your cards were empty, you were done eating for the day. It's a very simple dieting system. It's the same idea. So think of degrees of freedom as like these are all the cards that you have to spend, and each statistic that we compute, we spend one. So for this case, when we have, we're just talking about the sample mean, we spent 1 because we had to compute the sample mean in order to do this. So n minus 1, n minus 2, n minus 3 will show up. And that's why in the formula for variance, we divide by n minus 1 rather than n, because we had to spend one card, spend 1 point to compute the sample mean. Whereas if it's just the mean, we haven't spent anything yet, so that starts at n. So you'll see this throughout the course as well. There's going to be two different versions of degrees of freedom, numerator and denominator. This is denominator, and it's always based on number of people in this course. All right, so putting it all together. So standard error of the mean. That's our magic thing that allows us to go from one sample into talking about the expected behavior of multiple samples around some population mean null hypothesis. If you know the population standard deviation, you can use that in computing the standard error. If not, you use the sample one. Especially if you use the sample standard deviation, you need to pay attention to how many people you have, because your sample standard deviation tends to be underestimated, too small in small samples. So in almost everything that we're going to do, we're going to use t as our test statistic that locates whatever statistic that we have from our sample onto some kind of standardized distribution. And we'll get an exact p-value that goes with that t that tells us what is the probability of observing what we got if the null hypothesis is true. So what is the probability of this sample mean if the population mean is this? That's the instance that you guys get to practice in your first homework, which you should now be able to do. So, ta-da. Okay, let me go back for 1 second. All right, let me pause. Questions? Do you want to
Yeah,
see?
I have a quick
Yeah,
question.
okay.
So when you're saying that we have to do this for our homework, this is not something that SAS or Stata is going to compute for us.
Oh, yes, it is.
Oh, it is.
Oh,
Okay.
absolutely.
Oh, thank goodness.
Yes. I'll show you how to do it. I'm glad you asked. That was actually a
Oh,
beautiful segue into the
okay,
next few slides.
wonderful.
Yes,
Okay.
yes. Stay tuned. Stay tuned.
Okay.
I'm getting there.
Oh, will do.
Yeah. At what point is a sample big enough for the z to be fine? Well, the colloquial wisdom is 30. That's a number that I've heard people just say. But if I go back to, let me find this picture here, it depends on how confident you want to be. So if you look at where the curved line meets the dashed line, that's where it doesn't matter if you use t versus z. And if you want to be stricter, only 1% unexpected, then 30 isn't enough. So generally speaking, T is the safest strategy. At some point, it doesn't matter, but what that point is depends on a lot of things. So that was a question on that. Okay, so let me give you a real world example because all of this is like, okay, fine, but when would I ever actually use this? Is anyone thinking that? It's okay to admit it if you are. Yeah, like, okay, Lisa, this is great, but like, I have a life to lead and I'm hoping that this information fits into it somehow. Yes, I'll give you a real example. So here is a published paper from a couple years ago. I'm one of the authors. This is Mabel Rice's work. She studies specific language impairment, which is a tendency detectable in young children, but it continues throughout adulthood, of folks that otherwise have no cognitive impairments of any kind. They're just not good at grammar. So rules of syntax and past tense and present tense and agreements of verbs, singular, plural, and that like they just it's not good for them. Mabel's probably listening to this going, no, she's ruining my research. But for our present purposes, that's a good enough definition. And it turns out that twins are more susceptible to having this specific language impairment. And so one of her lines of research is trying to understand to what extent is that a genetic thing because it's passed down through families, and to what extent is it environmental, like if you're talking to your twin all the time, that's somehow different than having a different kind of experience. So she and her colleagues here from this paper conducted a very large scale sampling of twins in Australia. And twin studies oftentimes don't use standardized measures, apparently, and so this is one of the first studies to make a point of using standardized measures where there is a population value that you know, right? Because they're all standardized to where the mean is supposed to be 100 and the standard deviation is supposed to be 15. And so the point of this table in particular, research question number 1, as I recall in the paper, is to what extent is there empirical evidence to support the idea of a twinning effect, that these kids relative to singletons are delayed on average. Evidence of a delay would be this sample's mean being lower than the population mean it's supposed to be. So this is one of like the 9 outcomes in this paper. This is a measure of vocabulary, the Picture Peabody vocabulary test, given at age 4 and 6 to MZ and DZ twins, so whether or not they're fraternal or identical. And we have different sample sizes across these. But here is the sample mean, for instance, for the 4-year-olds who are DZ twins. They had a mean of 96.78. Well, if this sample is taken from a population mean of sort of normal, I hate to say that word, but sort of expected variability, we'll play it that way, typically developing, the mean should be 100. So is this mean off enough to provide evidence that this is really unexpected? Like it's more likely to come from a different distribution than the one that we're expecting as 100? Well, because we have so many people, the standard error here is pretty small. It's 0.6. So here's my confidence interval around my mean. 100's not in it. So this sample mean is unexpected. It is below where it's supposed to be. The next one, for MZ twins at age 4, the same thing happened. For DZ twins at age 6, it actually went the other way. So age 6, they're actually doing better, significantly better than expected. The confidence interval doesn't include 100 because it's above it instead. And age 6 for MZ twins, the confidence interval here does include 100, meaning that a mean of 100.28 would be reasonably expected if the population mean were actually 100. So the conclusion that they came to in the paper, because this is like I said, 9 different measures, is that there tends to be a twinning effect by age. They observe it at age 2. That was an earlier paper. And 4, it starts to go away by 6. By 6, it becomes more inconsistent and they become more like typically developing children. But if I just look at this one result here, I can compute a confidence interval that where these numbers came from is right here. And by the way, I'm showing you the math just to show you how to put the numbers into the formulas, but I did not do this. SAS did this for me. SAS did this whole set of tables, and I'll show you how in just a second. I have 770 degrees of freedom because I had 771 people in this condition, and I only had to compute one sample mean, so I've got 770 points left here. So the critical value for where unexpected starts is basically the same thing as Z, so 1.96. So this confidence interval came from my sample mean estimate times the critical value that tells me where unexpected begins, 95% in this case, times the standard error. The test statistic relative to an expected mean of 100. Internet is unstable. I'm pausing. Am I back? We're good? Okay. All right. So my t-test statistic. Note the formula is exactly the same. It's the sample mean minus the population mean divided by the standard error. So T and Z are telling you the same idea. How many standard errors off from expected are you? And in this case, it's like 5. So a t of minus 5 would happen, and this is the p-value that's provided on the output, less than 0.0001. So you'll see this sort of result happen in your output, 0001. That means a t-value as extreme as this. So finding a sample mean that's 5 standard errors away would happen less than 0.01% of the time. So this is a reject the null hypothesis. This sample mean is significantly lower. And I know it's lower because I'm looking at the number and I'm saying 96 is less than 100. Significantly so because it would happen less than 5% of the time. P-value less than 5%. Here is the t-value that goes with each of these results. So 2 of them are significantly negative. One of them, the third row here, is significantly positive, and the last row is a t of 0.35, which corresponds to a p-value of 0.72. So note that I have different n's in each of these cases, which means that I have different degrees of freedom. I have different sample means, I have different standard errors, and all of that can be put onto the same t metric. So t is like the great equalizer. It takes all of that information, it puts it onto the same scale. So the first result is 5.5 standard errors away. The second result's even more extreme, 6.7 standard errors. The third result is 4 standard errors above, and the last one is only a third of a standard error. So well within expected territory. You would expect a mean of 100.28, like 72% of the time. So that's well within the middle here. Now, how to make SAS and Stata do this for you. Thank you, I think that was Maria, for setting up this question for me. Proc t-test in SAS. Yes. So the information that you would have to feed into this to use it, in SAS, always what dataset are you using? So this is from example 1, and I go over this in, I think, the second video. You would need to change this to be homework 1. HO, that's your null hypothesis. Where do you want your stick planted? Maybe it's a flag. Stick or flag? I don't know. Either one is my arm doing this thing. So where do you want your flag planted? Okay. In this example, I'm using the example 1 data to look at years of education, and I'm testing the mean years of education against 12. So let's say that I believe that my population should have a high school degree on average. I want to know whether or not my sample looks like my population. So 12 years of education. Sides. That's two-sided, meaning do you want to take your unexpected region and allocate it to both sides? Your result could be too high or too low. The answer is yes. And then alpha, where's your cutoff for where unexpected begins? So that alpha level combined with your data then tells SAS what the right t-values are to denote where unexpected starts. And the results that, or wait, one more thing here. CI equals equal also gives you a confidence interval around your standard deviation in case you wanted to report that. And by default, it spits out a bunch of pictures, none of which are helpful to this point, so I shut those off. And then var stands for variable. What variable do you want this test for? It's education in the example 1 dataset, and then run is it saying please. So we get these 3 tables. Gives you the n sample size, gives you the sample mean, the sample standard deviation, and the sample standard error. It gives you the minimum and maximum values. It puts a confidence interval around the mean. So if the mean is 13.8, about 2 standard errors roughly on either side of that gives me an interval of 13.6 to 14.0. I don't have to look at anything else. I know the answer right now. Is this sample unexpected? Aberrant? What do you think? If I expect 12 is the right answer of the population, is my sample within expected fluctuation or no, it's unexpected? So we have couple votes, expected or unexpected. 12 is expected. Does my interval contain 12? Nope. So this is unexpected. So I know right now because the mean is not in the interval, that's a reject the null hypothesis. More precisely, the last box here gives me my degrees of freedom, which is n minus 1. my t value, that is my test statistic. And that tells me that my sample mean is like 16 standard errors away from where it's supposed to be. It's supposed to be 12 according to my test, and I actually got 13. So my population mean is lower, which means my sample mean is higher. My sample mean is higher than the population mean. It's significantly higher because I have crossed the 0.05 mark. So this thing right here, PR greater than T with the brackets around it, that's SAS for p-value. Literally, it says probability greater than the absolute value of T. That's what the bars mean on the side of it. So that's setting you up for a two-tailed test. So that thing right here, PR greater than T, that's your p-value. That's the probability of finding a sample mean of 13.8 if the population mean were 12. Not likely to find something so different. Okay, with me? Okay, state of people. Yours is called t-test also. State of people don't have to worry about changing the name of their data set because only one is open in memory at a time. You do have to change the name of the variable, and what you want the null hypothesis to be for the population mean is set after these two equal signs, and that's not a typo. They are two. In Stata, conditions meeting a values meeting a condition have two equal signs, like if this is true, sort of. So you're testing whether or not the mean of education is equal to 12. And level 95, that's the same thing said backwards as alpha 0.05. Of course, right? So it's 95% expected, confident, 5% alpha, unexpected. And it gives you the same information, albeit in a slightly rearranged way. Instead of n, it calls this column observations, but mean, standard error, and standard deviation. Note these two are backwards relative to where SAS puts them in terms of the alignment of the columns. It gives you your t-test statistic right here, the degrees of freedom for the test statistic, and then it gives you actually all three versions of your hypothesis test. The one in the middle, where it's exclamation point equal, that means the two-tailed test, where you're saying different than 12, allowing for too low or too high. And Stata puts the p-value at 4 zeros. That just means less than 0.0001. So it's the same idea as what's reported in SAS, but SAS puts the less than explicitly. I wish Stata would do that. And then if you want the confidence interval for the variance, that's this next little piece of information, but I didn't ask for that. Okay, how are we doing? Feel like you can do this? Yeah, we'll find out, right? There's no other way but to give it a try. So this process of, okay, what did we get? Where is it relative to expected? And is it too different to be expected just by chance? That we're going to repeat across the semester, that idea. Lecture 2, which will start next time, is going to be the idea of testing bivariate associations. So if I have a measure of association between two variables, relative to what I expect that association to be, which is almost zero, almost always zero, I should say, where is what I found relative to that? And our friend T is going to show up because life is just better with beer. T is going to stay with us. There was a T-shirt that said that when I lived in Lawrence, Kansas. There was a local brewery that had that as their slogan, and I thought that was a good slogan. In the interest of making sure that we don't get too far behind, I'm going to record offline the rest of the slides in here because I'm not asking you guys to do that for homework. I just want you to have it sort of in your arsenal. And so we'll be able to start lecture 2 and example 2 next time. How's that sound? Good. Okay. If you are finding yourself I wouldn't say bored with the material, but seeking a challenge, let me know because I know some of you have had this stuff before and you're like, I got this, it's okay. And for some of you, it's brand new and that's okay. Let me know if you want some extra things to work on or do, and I'd be happy to give you some additional materials. In terms of software, if you come to this class knowing another software program such as SPSS, that would also be a good opportunity to practice these things, is to try and learn how to do it in that package also. That way you have another line on your CV. Especially learning how to do things in R would be beneficial. So there's always things that you can do above and beyond this, but if you get through homework one, then I'm happy with just that much. So, okay, so we will come back on Thursday, start a new topic. I'll let you know when the video is ready that finishes this one. It shouldn't be too long. Okay? All right. We call it a day? All right, go enjoy this beautiful weather. I will see you Thursday. Take care of yourselves.